And are we recording is my other question. That button happened.
We are recording.
Yay!
We are started.
Fantastic. Beautiful. All right, so it is 4 o'clock Sunday afternoon. We are in late September, September 26th, and we are talking about exam 2. So some of you guys submitted questions, which is fantastic. So I have some of those hanging out up here. So the things I have first are some of the general things of what's going to be happening on the exam and what's going on. So this did change a little bit from the first syllabus. We did send you guys out a new draft, but basically what we're looking at for exam 2 is we are looking at chapter 4 and chapter 6. Originally, we had also put in a smidgen of chapter 5, but we are honed in on chapter 4, chapter 6. So there's a couple of things that are getting shoved to exam 3. There's one more part of that, which is there's 2 sections in chapter 4, which are 4.6 and 4.7. And those are actually going to be exam 3 as well. So you likely just didn't hear those talked about in class. Those specifically have to relate. There's a periodic trend that relates to ions and what happens to actually the size of ions. That's going to be on exam 3. And there's also what happens to electron configuration with ions, and that's also going to be on exam 3. So essentially what we wound up doing is focusing on neutral atoms. So oftentimes you are going to see the words neutral, ground state, atom. That won't be the only cases we use, because we could still potentially use excited states, but you will certainly see these words a lot. See this a lot. Not always, but a lot. So that's the general idea of what's going to be on the exam. So 2 chapters. As far as where will most of the topics for the test come from? So this is always a good question. We are writing the exam now. So based on what's been assigned, we're aiming for slightly more questions in chapter 4 than chapter 6. And my voice went up with that kind of question mark, because basically whenever we assign topics, that's not a guarantee of what the end exam will look like. So we're aiming for a little more on chapter 4 than chapter 6, mostly because y'all will have more time and have more exposure with chapter 4. So right now aiming for a little more on chapter 4 than chapter 6, but kind of like a 60-40 split. So you guys might actually feel like it's more half and half with where you spend your time, but we're aiming for a little bit more in chapter 4 than chapter 6. I got asked a question about any conversions or calculations on this test. So for conversions, that one's easy. No. So we're not doing conversions. They will be back on exam 3. So I know that there were some conversions that people struggled with a little bit in exam 1. Those are definitely still worth going over because they will come back on exam 3 and 4 and 5. But you at least get a little bit of a reprieve on this exam. So exam 2 traditionally doesn't have a lot of math. As far as any calculations, and I know some people will tell me that this doesn't count, which is fine, but you do need to be able to add and subtract electrons. And I mostly say this because if y'all ever watch me do Lewis structures, I usually do Lewis structures with a calculator, because when I'm put on the spot, if you actually make me subtract like 32 minus 4, there's a chance I'll get it wrong if I do it in my head. And I know that sounds really silly, and I realize that shouldn't happen, but you know what? I know myself, it does. So it's really common for me to go ahead and have a calculator to add and subtract electrons. Not joking. So again, as far as any calculations, that would be really your only calculation for this exam, which makes life a bit easier. Time be the same? Yes. So basically all of your exam procedures will be the same. So you're still going to see the exam in section 701. That will still be the same. You'll still have 90 minutes. That will be the same. We're still aiming for 30 questions. I don't know if y'all saw last time, but we wound up with like 27. But we aim for 30. See how far we actually get, but we aim for 30 questions. So all of that is going to be the same. So a lot of the things that y'all experienced in that first exam, we will maintain and keep the same. And then from there, I believe I'm into actual questions. We're going to do breaks about every half an hour starting at 4:15. So I'm going to chat a little bit about some more of the topics, just take a look at what we have. Most of the questions that we got initially were in chapter 4, which is not a big surprise. Oh, there was one more to talk about, which this one you may just not have seen it before. So somebody did ask, will we be able to access our responses and the correct answers to the exams? You should actually be able to see that now. So that, I have to admit, didn't go live until like Thursday night, which is later than we anticipated. But that should be available. The last person I talked to said that basically if you went into the 701 section and clicked on my grades and clicked on the grades, and then they said, then they clicked again. Here's the awkward part and why I'm not showing you is I don't have a student account. So I cannot actually show you how this one works. So if you're having problems accessing your grades from the first exam, you have a couple of options. One is to do an internet search, search looking at exams in Blackboard. So e-learning is the UT Dallas version of Blackboard. There's a couple of things that we have in there that's a little bit different, but essentially it should function just like Blackboard. The other thing you can do if you're still having problems is you can ask friends and see if other people have figured this out, as well as any sophomores, because we have a whole slew of folks that took our exams online last year and they're floating around. And then if something's really wrong, you can also contact e-learning at utdallas.edu. So yes, we do want you to be able to see your first exam and to be able to get that feedback and take a look at it. So if you're having problems with that, honestly, you are better off asking other people than you are asking me because I can't actually show you. So I've already told you guys, for better or for worse, the way that I think this should work, which is to go into the 701 section, click on my grades. Your grade should be there. It should be blue. It should be something that you can click on. And it should be able to show up that way. So if it's something else that's not working, then I don't know. The other couple little things I wanted to touch on. So someone asked me about quantum numbers, and this one I actually will talk about because quantum numbers actually tie really beautifully to electron configuration. So while there are things from exam 1 that we will leave in exam 1 and we won't use it again until the final. So your final exam is cumulative. So your final exam will involve things from the entire semester. Quantum numbers are tied beautifully to electron configuration. So quantum numbers are something that you might still want to brush up on if those gave you trouble on the first exam. So we will actually talk about those this evening. Wavelengths and how to calculate them, these are the ones that will be on the final. So anything that involves your wavelength, I'm going to write the de Broglie equation, or the speed of light is equal to wavelength times frequency. So any of these things are things that if you're struggling with them, you're definitely still welcome to ask about. I'm not going to address them tonight because we're going to focus on exam 2 material. So anything that involves wavelength is going to be on your final exam, but actually will not come up on any of the subsequent exams. So anytime you're curious about like which topics tie into the next exam and which ones do we either leave behind or leave out for a little while, also good questions to ask. So one more thing on that note is things like the moles to grams. This is something that will come back on exam 3. So moles to gram style calculations will come back, but they, again, you get a little bit of a reprieve. They won't be on exam 2, but they are on exam 3. And I had one more thing in here. We'll talk about Lewis structures and how those can be assessed. Someone did ask me about lattice energy. Lattice energy was the other thing that actually belongs on exam 3. That is a chapter 5 topic. I actually really like it. It's a fun topic, but it's a chapter 5 topic. So in a similar way, I got asked a couple different questions. Valence electrons, we want this on exam 2. This one we absolutely want. But photons, quantum theory, most of this stuff is stuff that will be on the final. So we will leave photons and quantum theory. We're going to use atoms all semester. But photons, quantum theory, that stuff will be on the final. Molecules is basically a lot of Lewis structures. And once we do Lewis structures, and that is going to be exam 2 material. Okay. So I'm going to go ahead and take just a little bit of time to start talking about quantum numbers. I'm going to take a break about 4 minutes, but we can go ahead and show you how quantum numbers tie into electron configuration. So for example, got periodic table. Oh, it's like I planned this. So essentially, we've been talking about things like electron configuration, but we talked about perhaps the notion that we had an S block, that we had a P block, that we have a D block here in the middle, and an F block down here. If you'll remember, those all relate to values of L, and these also all represent then different subshells. So the difficult thing is that when we start to talk about something like the 2p subshell, this language is left over from quantum numbers, where we could talk about the 2 being our value of n, where our p should relate back to a value of L. And even the number of electrons that are housed in it relates back to our values of m sub L. So the fact that I should have 3 orbitals, which then relates to my 3 values of m sub L. -1, 0, and +1. And the fact that then, because I have 3 orbitals, this will house 6 electrons. So most of the parts of quantum numbers that we need to bring forward is the language. So this idea of talking about shells, subshells, orbitals, that all goes back to quantum numbers. That's where we first talked about it. So it may very well be that at this point, you're so well versed and so confident in what a subshell is, maybe you just forgot that that's technically belongs in quantum numbers, but it's just to remind you that these are still things that connect back really, really well. So while we get really comfortable referring to this as something like the 2p subshell, realize that we could also talk about things like if the n equals 3, L equals 2 subshell is full, which of the following, oh, sorry, I need that phrase that I mentioned we were going to use a fair amount. Full in a neutral ground state atom. Which of the following atoms might this be? And we could give you options. like hydrogen, carbon. I have to look back up for a minute. Bromine and neon. So there are my three options. So here's my question. If n equals 3, L equals 2 subshell is full and a neutral ground state atom, which of the following atoms might this be? And what we would expect you to do is essentially translate that this n equals 3, L equals 2 really is referring to 0, 1, 2, 3, S, P, D, F. This is actually referring to a 3D subshell. So essentially it's promising that the 3D subshell is full. So full being all 10 electrons. So I probably should have thrown in one more thing in here like iron. So then as I go to look at my periodic table, I can go ahead and take a look, and here's hydrogen, which certainly doesn't have any d electrons. It's way at the tippy top. Here's carbon, also not going to have any d electrons. Neon, nice full p subshell, but no d electrons. Iron, at least we're getting into the d subshell, but it's not full. And the question wanted full. And then the last one I gave was bromine. And so bromine hanging out here would require you to know electron configuration a little bit as far as where do we fill up first and where do things go from there. But essentially it would use quantum numbers to still ask you a question about electron configuration and to identify atoms based on it. So that's my one kind of general warning is that there are some things in quantum numbers that we likely won't ask you about, but you still need to be comfortable with them, especially in the language. And I've gone over the 4:15 mark. So any questions that came up in those first 15 minutes?
Hello, yes, we do have quite a couple, but I will start with the ones that rolled in the beginning.
Great.
So first question is a half full S subshell stable even though it only has one electron?
So one of the places where this question comes from is we spend a fair amount of time talking about exceptions, and that a lot of our exceptions are either coming from, grab my periodic table. Hey, periodic table. So we have both exceptions in electron configuration for things like chromium and molybdenum and copper, silver, and gold. So we have some variations in electron configuration because the half-filled D subshell or the full D subshell is so much more stable that that extra stability results in a different electron configuration than you might expect, where essentially the S subshell only has one in it, but then the D subshell steals the rest. So this is D, this is S. This could be 4s or 5s. We'll go ahead and pick one. And we also see a similar issue when we get into ionization energy and electron affinity, where there are variations in ionization energy or electron affinity because of the stability of a half-filled P subshell. So you see both a half-filled D subshell and a half-filled P subshell reflected in exceptions to what we would usually think of. Here's the thing. A half-filled S subshell does have some stability. It's not that it doesn't. The difficult thing is that, one, usually any trend we would see, actually before I go into that detail, the bottom line is actually going to be it's at an unfortunate location because it's either going to be falling after a noble gas configuration as we're on the periodic table, or it's also right next to having a full subshell. So essentially, a lot of the trends you're going to see that would show or demonstrate any stability that involves a half-fill S subshell, there's usually other things that are going to overshadow it. Because the other thing that is true And we do see it. It's just not, but usually we've found a different name for it with the p subshell, is that usually your filled subshell will give you more stability than your half-filled. And again, this is something we don't usually get into the numbers involved in this because we're just trying to teach y'all overarching trends. But this is one of the problems with looking at the S, is because it's only that one electron in a half-filled to that other electron in the filled, a lot of times you just don't see the trend show up because there's just not that many electrons hanging out. So does it have stability? Sure, but the S is so small and there's only 2 electrons there that you usually don't actually get to see that reflected anywhere that we care about. That's going to be my answer. Does it have stability? Yes. Do we actually ever notice it? No. You can actually notice differences in the full subshell though. So there are actually some places with ionization energy that you can actually see the difference in the full subshell. So the full subshell of the S you actually do see in ionization energy. Full subshell, more stable. I'm just going to put ionization energy. You can actually see that in the graph for ionization energy. Let me grab that. Oh, let's go to the next question. We'll get to ionization energy later.
Okay, so the next one that rolled in, if you added a valence electron to a noble gas, would it then have an extra core of electrons and 1 valence electron?
Okay, so there's been a lot of conversations about exactly what a valence electron is. So when we say valence electrons, these are supposed to be the outermost electrons. And that's one word. And typically what we're looking at is we're usually looking for the highest value of it. The thing is that when we're talking about that definition then of valence electrons, people then get a little bit like, but what's happening when we either add some or we take some away, and then how do we really define valence electrons? Here's the thing. The main reason why we usually want to talk about valence electrons, the reason why they're useful, is to talk about essentially our expectations for the neutral atom. So we usually care about what sort of chemistry might happen. Those are some of the reasons why we're interested in valence electrons, is they're usually going to help us determine how a particular atom is going to act. That's why we want them. That's why we care about them, is they're going to give us ideas about what that particular atom might do. As far as them talking about, so what happens if I add an electron, what do we call that then? Realize that, first of all, we would then be talking about valence electrons in an ion. And the first note is that usually once you're in an ion, this then has typically different properties. From the neutral atom, because it's going to have a charge. So while we can still talk about valence electrons, one of the things to realize is that the moment that you add or subtract electrons from an atom, oftentimes the most important thing then is the charge, or then is how that's going to act differently. We don't expect a sodium ion to act the same way that we expect a neutral sodium atom to act. They act very differently from each other because of their valence electrons. In the same way, the person's asking about a noble gas. And a noble gas by itself is very stable. A noble gas with a negative charge wouldn't be nearly so stable. It's not going to want that electron at all, and it's going to be really reactive and ready to get rid of it. So I suppose what I would go ahead and call it, so this is me trying to think this through as I'm going along. So essentially, if I had neon, because it's a relatively small noble gas to draw out, I've got 10 protons in here. That's my nucleus. And then I'd have 2 electrons in my n equals 1, and I'd have 8 electrons in n equals 2, and then I would have 1 lone electron in n equals 3. So what would I call that valence? Would I call the electron in the outermost shell at n equals 3 a valence electron, or would I call all of the electrons at n equals 2 at n equals 3 valence? Huh. You know, actually, I can imagine all of the instructor team arguing over this question. It's frankly what I can imagine. I can hear it in my head. I can hear the different voices of my colleagues arguing. Because I'd have 1 electron here, I'd have 8 electrons here. Then the question is, does the anion neon have 1 valence electron or 9? And honestly, I'm going to send my colleagues an email and ask them, because I have to admit I'm not sure. Because I know what I would say, because frankly, if you go back to the original definition, then you're stuck with 1 electron as a valence electron. But valence electrons of ions, we don't usually do for anions, especially a situation like this, because this is just so terribly unstable. So I'm going to go with terribly unstable. Because usually the place where you do see this, so this is a question that came out of the chat, and this is honestly not something you usually see. What you usually do see, is something where you have sodium, and sodium then has 11 protons in its nucleus. So then it's going to have an n equals 1 with 2 electrons, and it's going to have an n equals 2 with 8 electrons. And when it's neutral, sodium then has that n equals 3 and 1 electron. So when sodium goes from a neutral atom with 1 valence electron, and then it goes and it loses its electron to become a positive sodium, we actually say that then the sodium ion actually has no valence electrons. Because what you've done is what we cared about is that outer valence electron, and now that it's removed, it's essentially gone. So sodium plus has essentially no valence electrons because you removed the only valence electrons it had. So actually, given that, I think I actually can come back and answer this. If sodium plus has no valence electrons, I think I'd actually go with the neon one being 9. I think you would actually wind up counting all of them. No, I just see us arguing over this, honestly. I just sense arguing. So I'm like, oh, but the value of n changed. I understand the value of n changes here, but that doesn't, Yeah, so anyway, so sodium, when you remove electrons, we would just talk about the fact that there's no valence electrons and that then you only have the core left. So yeah, I will bring up the noble gas, a noble gas anion to my colleagues and see what they say, and prepare myself for a long conversation. Other questions?
Okay, so the last 2 I'll ask for now will be over exam details, so everyone's on the same page.
Right.
But the first one, is there an exam review packet which tells us what exactly we need to know, or with example problems?
So we are a university and we do not prepare you guys like you did in high school. So we, aside from telling you what sections of the textbook the exam is over, that's really all that we do. So we do not give you guys an exhaustive list of topics that may or may not be on your exam. That's not something that we prepare. Maybe some of the other instructors do that. I have never done that. So maybe some of the other instructors do. Maybe your PLTL leaders or SI leaders or peer tutors do that, but that's not something that I do. As far as a list of questions, I've gotten that response a lot. So we have the end of chapter questions. So there's questions at the end of the chapters to help y'all look at different language that might be used to help you guys think about things in a different way. So we have end of chapter questions that we recommend, but we don't have necessarily ones that we write from scratch. Y'all, it's all we can do to put the exam together on time, let alone come up with more practice questions. So yeah, no, just all we do is basically tell you guys which parts of the textbook it's over, talk about where those sections are in the notes, and then talk about potentially end of chapter questions that might be helpful. But that's it.
Okay, great. And then the last one before we can proceed, just making sure someone wanted to ask if exam 2 will cover 4.6, 4.7, 5.1, and 5.3 in the chapters.
No. So going back. Oh, come on, internet. There we go. E-learning. Okay, so to show you guys, at least where I put this. So we did actually do essentially there's an adjusted schedule. So for my course, I put it in the course homepage and how the course works, because that's where the syllabus is. And so there is a PDF file that essentially has our academic calendar on it and updated. So exam 2 is chapter 4, 4.1 to 4.5, and chapter 6. And it actually has moved than where the other pieces are. So section 4.6 and 4.7 will be on exam 3 along with all of chapter 5. So we did move things. So things did get moved from where we were originally planning them. Essentially, what happened to most of us, I assume it was all of us, but what happened to most of us is most of us didn't start chapter 4 before the last exam. On the original syllabus, we had chapter 4 starting like Wednesday, September 15th, but very few people actually did that in their class. And so we wound up shifting and moving things to better represent where we really were. So that did change. But there's our updated schedule. Then we get pretty close to back on schedule then for the rest of the semester. Okay, so is that it for now for questions?
Yes, we can continue.
Okay, sounds good. Back to OneNote. So we were talking about quantum numbers and electron configuration. We talked about some of the exceptions. We talked about valence electrons this little bit. So one of the other questions that got asked was on electron configuration, and most specifically, what comes first, F or D? So this one comes up when you were looking at the periodic table, and let's say we were going to write out the electron configuration for, we'll do polonium. We'll pick a metalloid just for kicks and giggles. So I'm going to go ahead and use the noble gas shortcut for this, because otherwise this gets very long very quickly. So I can start with xenon, and then I start off with my 6s2, and then actually we start to have a problem like right now, which is, do you go ahead, because the little cutoff for where the F block is, so I think in Dr. Bacon's video, what she did is she went ahead and did 5D1, and then went ahead and came down here, which this is the 4F, and then went ahead and did 4F14, and then went ahead and after you go 4F14, then you come back in here, and then she did something like then 5D9, And that gets you all the way through this part. And then we're finally back in the P block. And we're finally back to 6p4. And then, but then essentially you just want to talk about 1d subshell, so you've got to combine these. So then the grand question is, which one comes first? And I know Alex has major opinions about which one comes first. As a teaching team, we don't. So what we do, so I'm going to do it the way I usually do it, which is I usually put the F block in so I don't forget it. For, you know, in all sincerity, that is my reasoning. I think also when I was in high school, that's what they taught me to do. But now I have carried that on because I'm always somewhat afraid that I will forget to do the F block because it's way down there at the bottom of the periodic table. And part of my brain is just like, don't forget it's there. So this is my habit. Now, what's going to happen on your exam? So I know Alex has opinions. So we are going to be looking for something that at least combines everything. What's going to happen on the exam essentially is we're not going to make you choose. So it's entirely possible that on the exam, you would be trying to pick the electron configuration for polonium. But if that was the case, your options would look something like this. Six S2, 6P4, xenon, 6S2. We'll go ahead and put the 5D first. Why not? 4F14, 6P4. So granted, I know there's only 3 options and we would give you more than that, probably changing up the noble gas. But essentially, we're not going to vary this portion. So this 5, so while the which one should come first, the 5D or the 4F, that one really is something that you'll see written different ways, and different people have different opinions on which one goes first and which one goes second. For us, we're basically not going to test you on that. So you'll need to know, are those subshells full? You'll need to know that they are there. But as far as which one goes first, we're not going to give you options that would allow that. And if it's any version of fill in the blank, then both of those would be accepted. So that's one of those things that I know that one comes up a lot. And that's also one of those that, frankly, the other thing is that sometimes you've learned something when you were in high school, and this is not important enough for us to untrain you out of. So if you've already learned from high school that one of them comes first and that's just always the way you do it, that's fine. That's totally fine. So this is not something, this is not a hill that we're willing to conquer. We'll just leave that one alone. But that's what you'll find. You'll find on the exam is that we basically won't give you options that are exactly the same, but move the 5D and the 4F. We could give you one that names it incorrectly. So we already figured out this is the right answer. So coming up with what another wrong answer could potentially look like, we can still do xenon, 6S2, 6D10, 6F14, 6P4. So I mean, we could do that, but that's also wrong for other reasons because the N value is wrong. So we addressed that one. Where else was I in electron configuration? Lots of stuff over about trends. Anything else over electron configuration? No. Okay. So there was this other question that comes up in different ways. How do we know if an element is stable? What does that tell us about the element or the subshell exactly? So this one is, oopsies, a good question. I wanted to copy it, not delete it. So As far as what's going on here, so whenever we're talking about stability, anytime that we say stable, what we usually are talking about is we're talking about lowest, or lower in energy. So anytime that we're dealing with stability, lower in energy is more stable. So oftentimes you'll hear us talk about that in the same breath. We're looking for the most stable state, the lowest energy state. They are the same thing. Lowest energy, most stable, same thing. As far as knowing if an element is stable, this is again actually where that idea of neutral ground state atom comes back. Which is to say that oftentimes we're talking about ground state, and this is the lowest energy state. So the short answer to how do we know if an element is stable, usually we tell you. Frankly, usually we just tell you. Now we can do things with excited states, so that is an option. But if we're going to do excited states, usually we have to provide those for you. So we put instructors could provide an excited state. But we would not expect you to come up with one, essentially because there's an infinite variety, an infinite number of excited states, not variety, infinite number of excited states. So we could do something where if I'm talking about something that has 8 electrons, so this would usually be oxygen, I could have my 1s, and then I could have my 2s, 2, 3, and my 2p, 1, 2, 3, 4, 5, 6, 7, and I'm going to put one up here. 1, 2, 3, 4, 5, 6, 7, 3, 4, 6. There you go. So there's my, here's an excited state. So we could tell you, hey, this is an excited state. And then we could even perhaps ask you then to write the electron configuration for the given excited state. So, or we could give you the electron configuration and ask you if it's an excited state. So you could analyze a given excited state. 2p4, 3s1. And that would be compared to something like 1s2, 2s2, 2p4. And so then the question would be, which is the excited state? In which case, again, the thing that's going to look normal to you is going to be neutral ground state. So you're looking for the excited state. So you're looking for the thing that looks weird. You're looking for the thing that looks wrong. But it's not necessarily weird or wrong. It's just different because it's an excited state. And what we're asking you to do usually is provide the neutral ground state. So hopefully that helps clarify a little bit of things. I know as soon as we get into excited states, everybody gets kind of nervous. And really the thing with excited states to realize is that they're not the norm. They're not the usual. And we have to provide these to you. Because, that's why we had this example down below where I drew some out, and then you can analyze and tell me like which one of these is an excited state out of all of these options. Because again, there's a lot of options when you're looking at potential excited states. And so we would have to provide you with what those might possibly be. And I think part of what they're talking about is looking at half-filled subshells, and we'll talk more about those when we get into the periodic trends, which is where we'll head next. But it's about it's 4:44, so I'm close to my 4:45. Are there any questions that have come up so far?
Yes, so I'll be asking 4 right now. 2 will be over ionization energies, and the other 2 will be over electron configuration.
Okay.
So in relation to electron configuration, the first one, does 3D have higher energy than 4s?
So I'm pretty sure I spent a lot of time telling you that in electron configuration, it doesn't matter and we won't test you on that. So if it's just really bothering you which one is which, pretty sure my bottom baseline point was that it didn't matter. So I'm not going to answer that one because y'all have more important things to worry about than which order do those go in electron configuration. That was the entire point of me doing that it did not matter. What's the other question about electron configuration?
Gotcha. Okay, if something like copper got an extra electron, would the electron go in the half-full S subshell or would it go in the P subshell?
So I'll go ahead and answer this one. So I'm going to remind you that electron configuration of ions, which is technically what I was just asked, is on exam 3, not exam 2. But I will, since I avoided a different question, I will go ahead and answer this one. So when you're looking at copper, here's my periodic table. So this is the kind of question that we could do on exam 3. But since it does talk about exceptions, we'll talk about this part at least. So the electron configuration for copper, it is one of the exceptions we do expect you to know. So we would expect you to actually know that the correct electron configuration for copper is 4s1, pardon me, argon. Eraser. Is argon 4s1 3d5. So this is the correct electron configuration for copper. Yes, it does have this weird thing where there's 4s1, but this is one of the exceptions that you're responsible for. So this is the correct neutral ground state. Electron configuration for copper. So there it is. So the question then is, if we were, if we're going to add an electron. Oh gosh, copper doesn't do that very well. So usually we would ask about cations because that's what metals typically do, is form cations. You guys keep wanting to add electrons to things that don't usually get electrons added to them. So you guys are asking me where the electron goes if you add one. So in that case, we're going to continue to play the stability game is what the argument I would make. So if we're starting off with this, I'm going to argue that the best way to keep copper being as stable as possible would be to go ahead and complete the, oh, pardon me, it's not 3d5. They're probably correcting me in the chat and getting mad at me that I did this wrong. 3d10, it's copper, not chromium. Sorry, copper. 3d10. Sorry guys, you guys should be correcting me in the chat and yelling at me. I've mentioned this to some folks. This is one of the things I actually miss doing things in person, because even with the de-densification, I still don't get the same effect. Usually when the room's actually full of people, like the noise level rises. Like even if nobody actually calls me out on it, like the number of people asking like, what is she doing? What is happening? that noise level usually rises. And so I usually get this instant feedback that I have done something wrong very, very quickly. But yeah, so if we're going to add an anion here, then I'm going to argue that instead of going into the P subshell, we're going to go ahead and go back and fill in the S subshell. So we can still follow, so even though I realize that this kind of is an exception to Aufbau, basically when in doubt, you're going to go back to the rules that you know. So even though copper is an exception in that its electron configuration has that 4s1 component to it, when you're then trying to think, well, what would happen if I did X, Y, or Z, you're going to fall back on the principles you know. So the Aufbau principle is that build up principle. And so then when we're adding one more electron and we're faced with which one do you want to go for, the 4s or the 4p, you're going to go ahead and fall back and go with the lowest energy first. Yes, I know copper is strange in that it leaves that 4s1, but that's to favor the greater stability of the full 3D subshell. So I'm moving on to ionization energy. What are the next questions?
Yes, so the first one about ionization energy, sorry. Can you talk about comparing elements of second ionization energy?
Oh, sure. I think I know what that means. So first of all, when we say ionization energy, realize that there's we're talking about removing an electron. So ionization energy is removing an electron, technically from the gas phase. So first ionization energy is where you have some sort of atom and it is going to an ion. The second ionization energy then is when you then are taking and you're removing the next one. And this is important because anytime you're talking about ionization energy, we're always removing one electron at a time. So we could keep going into third and fourth and fifth and just realize that all we're doing is we're removing the next electron and the next electron and the next electron. So all of these are doing electrons one at a time. So the question is about comparing second ionization energies. So a lot of times what we mean when we are talking about removing second ionization energies is we're usually trying to get at some of the major places we find big differences. So to be more clear about that, coming back up here to the periodic table. So if I want to talk about this having a second ionization energy, I might want to compare my second ionization energies of sodium versus magnesium. So when I look, here they are. Here's sodium and magnesium. So if I'm going to remove not just the first, so technically this is removing one from sodium plus versus magnesium plus, because we're removing the second electron. So when you're removing the second electron from sodium, that's going away from a noble gas core. So essentially, your first ionization energy in sodium took away its one valence electron. It only had one electron out there. Magnesium, though, had two. So when we're talking about our second ionization energy for sodium, sodium is now starting with only core electrons. So sodium removing an electron is removing just a core. That's all it has. But magnesium removing a second electron would actually make it get to a noble gas configuration, or it would leave it with only its core electrons. So essentially, sodium is going to hold on tighter because sodium only has core electrons left. Magnesium still has one valence electron left. So while in general, second ionization energies are higher than first ionization energies, So in general, if this is the same element, you would expect your first ionization energy for whatever element to be less than the second ionization energy for the exact same element, than for the third ionization energy for the exact same element. So you would get larger numbers if you were sticking with the exact same element. If we're changing elements, then usually what we're talking about is we're looking for, are we removing a core electron or are we removing a valence electron? So then in this case, what you would expect is you would expect the second ionization energy of sodium to be greater than magnesium. So my ionization energy for sodium should be greater than my ionization energy for magnesium. And that really is based on the fact that now we're removing core electrons. So I assume that that's what that question was trying to get at, because essentially in first ionization energies you'd be looking at something different, but in second ionization energies we might be getting down to those core electrons. I think that answers that question. I think we have one more question. Yeah.
Yes, thank you so much. And the last one, the overarching question from this one, it's kind of long, but I think they're asking about the exceptions to the ionization energy trend, like group 15 and 16 on the periodic table.
Oh, sure. Okay. So since we're talking about ionization energy, and we've been talking about this whole notion of half-filled subshells and what's going on with all of that. So one of the things that happens, and I think your textbook just has pictures that just have the P subshell for 5A versus 6A, or as the person was saying, 15 versus 16. But we're talking about these two columns. So 5A like nitrogen, for example, or 6A like oxygen, for example. So as we're going along for 5A or nitrogen, we should have 3 electrons. And those are just the ones that are there. Actually, I wanted those to be in blue. No. Oh, is it doing that thing already? Okay, hold on. We were doing so very well for such a long time. Okay. So 1, 2, 3, 1, 2, 3, nitrogen, oxygen, 5A, 6A. 1, 2, 3. Good. 1, 2, 3, 4. So when we're talking about ionization energy, we're still talking about removing electrons. So ionization energy is still removing electrons. In this case, we are still back on first ionization energy. So I know we did second ionization energy a little while ago. And in general, if we forget to specify which ionization energy we're talking about, the default is first. So if we ever just say ionization energy without clarifying, we mean the first ionization energy, unless we say otherwise. So essentially, my options here in first ionization energy, if I would be removing an electron from nitrogen, and that would basically break my half-filled subshell. So you basically expect nitrogen to have a little bit higher ionization energy, essentially kind of fight to keep your half-filled subshell. Like that's extra stability, so trying to get out of that stability is going to take a little bit more effort. Whereas when we look at oxygen or any of the things, any of the elements in 6A, removing this electron actually gets us to a half-filled subshell. So this would actually, removing yields, creates that half-filled subshell. So this is extra stable. So what you wind up seeing is that it actually does not take as much energy to remove an electron from oxygen as you would expect. So when we're looking at a graph, I think I've got all of them up. Yep. So when we look at a graph of ionization energies, what you should actually see is that while they're close to each other, you actually see a little bit of a variation in your group 5A and 6A. And that's what that is there, and there, and there. Is essentially where you're going along, and suddenly when you get to 6A, 6A actually has a lower ionization energy than you would expect. So 6A is a lower ionization energy than 5A. And the reason why I went ahead and brought the graph up is to show you that it is an anomaly, but it's not. Basically, you can see from the graph how large that anomaly is. So it is an anomaly since they do swap places, since 5A is greater than 6A, and it's not what you would expect, but it's not enormous. But the difference is there. And so we do often test you guys on that particular trend and the oddity in 5A and 6A. You can also see that, we were talking about the S subshell earlier, and you can actually also see this when you're trying to remove an electron from, becomes our 2A versus 3A. You actually see that same effect. So you can actually see the stability of having a full S subshell. So essentially this is the 2S and the 2P. And so when you could actually remove this one, so this is the configuration for boron. So you actually have boron having a lower ionization energy, because then as we remove this electron, you get the stability back from the full 2S subshell. So you can see some of those variations in ionization energy.
Okay.
Other questions? Yeah.
Oh, another question rolled in based on this, and they just wanted to ask if there are any other groups like 15 and 16 on the periodic table they should look out for.
Yes, 2A and 3A. So where 3A is lower than 2A, the boron and beryllium thing. So yes, that one. And I understand that you could probably try to make the argument that somewhere in the D subshell it's in there, but I don't know if y'all noticed when we did all of the different periodic trends, but we tend to focus on the S block and the P block, and we tend to just like draw the line through the D block and ignore the F block. And we will be consistent in doing that, because some of the transition metals just do kind of wonky things, and you can kind of see some of that wonkiness in here. So yes, we will pay attention to the S block and the P block, because those are nice, neat, and even. And if you guys are ever curious, I think it's a junior level class called Inorganic Chemistry, not organic, but inorganic, that does lots of stuff with the transition metals. Super fun, by the way, but different class. So yes, so 3A lower than 2A, this one you can also handle. This one's totally fine. We'll leave the D block out of ionization energy trends. Anything else right now?
Okay, I'll just do one more and then we can continue. But someone asked, why does tungsten not follow the 4s1 and 3d5 exception?
Nobody asked me that in class. I was so confused. So earlier we were talking about exceptions to the electron configurations, and you guys may have noticed that I circled 5 elements, and there is a 6th that makes so much sense that it should be one, but it's not. Tungsten actually follows the rules and is not an exception. As far as why, the person that would give you a very detailed description of why would either be Dr. Diekman or Dr. Seibert. They love inorganic chemistry much more so than I do. Forget if we've talked about this, but my background training is as a biochemist. So essentially, my PhD training is like here in the periodic table. Oh, and hydrogen. And I did some stuff over here. These guys are fine. I like these guys. I like the halogens a lot. They're fine. Sulfur's okay. Sulfur's useful. Phosphorus is great. I could really kind of take or leave a lot of the transition metals. I need like 3 of them, and then I'm happy and I'm done and I'm out. So questions like exactly why does tungsten follow the electron configuration rules when the other 5 don't? Really, the general things that I know are things like the lower you go in the periodic table, the higher in energies you're dealing with. So a lot of times what's happening is the lower you go, the closer together the energies are. That's actually something that we studied back in the last chapter, where it's easier to draw when all we're doing are values of n equals 1, n equals 2, n equals 3. The higher you go, the closer together the energies are. When you have multi-electron atoms, of course, then you have n equals 2, but you also have s and p. You have n equals 3, but you have s and p and d. And then you have to deal with the fact that the 4s is down here and the 3d is up there, and everything starts to overlap with each other because these lines get closer and closer and closer together. So because of how close in energies these are, that also means that based on stability, they start to swap places very easily. So exactly which one is more stable becomes something that you can sit down and calculate. Like we can get numerical values for the added stability, but looking at this, my best guess is that because we're so far in energy, and we start to involve the F subshell as well, that a half-filled D subshell just isn't worth the extra stability at that point. And I know that that sounds really arbitrary when I say that, but again, the hard thing is the lower in the periodic table, the closer together the energies, and without doing the calculations, you just start to have, what's it called when it's just not worth it anymore? Like diminishing returns, the law of diminishing returns. It's really like a law of diminishing returns where just the energy levels are so close together, that little extra stability you would get from a half-filled D subshell doesn't even out. So tungsten doesn't follow the rule. And yeah, Dr. Diekman or Dr. Seibert would probably give you a much longer answer than that. I don't know if it's better, but they give you a longer answer if you want to talk more about transition metals. Other questions so far?
And we are good for now.
Okay. So we went ahead and leapt right into ionization energy, and we did talk about the exceptions, which I'm glad that we did. One of the things that I do think is worth talking about is just to mention all of the periodic trends, so that we don't forget any of them. So realize that when we talk about periodic trends, when we're talking about the overall trend, we're usually just going to blatantly talk about going across the periodic table and then usually down the periodic table. So when we say across, we are talking about from left to right. So whenever we say across, we do just mean from left to right. So in general, as we go across, we've got really 4 periodic trends where we could talk about Z effective. As we go across, Z effective increases. Your atomic radius decreases. Your ionization energy increases, and your electron affinity increases. Now, again, I'm not pointing out any of the exceptions. This is why I got giant arrows and just drew the giant arrows. So this is the in general what happens. So this is ignoring the exceptions like we just talked about in ionization energy, and electron affinity has some too. As we go down, our Z effective actually decreases. Our atomic radius gets bigger. So our atomic radius increases. Our ionization energy decreases. Our electron affinity decreases. Decreases. Don't draw the arrow backwards. My brain told me that it was going the same way. And for some reason, it interpreted the word same as being, come on. There we go, kept my eraser. But apparently not that. Goes down. Also, it doesn't help in the classroom, which I'm super excited. I've finally gotten used to it. That's just there to stay, apparently. Oh, that's why. In the classroom, though, there's actually an eraser on the pen, and I can actually just turn the pen around, and that's my eraser, and it's kind of awesome. So I get to pretend in the classroom like I have a real pen in my hand and just flip it around and erase. And now I'm like, oh, this one doesn't do that. That's right. So these are, in general, the trends. So notice that a lot of them all go together. Atomic radius is the one that usually stands out. Realize, though, that this idea that my atomic radius is opposite should actually make sense, because what's happening here is as we go across, my nucleus is better at holding on to the electrons. So anytime we have our Z effective, our ionization energy, our electron affinity going up, what's really happening is the nucleus is holding on to its electrons better. And I am exaggerating this. So essentially the nucleus is doing a better job of holding on to all of its electrons. And so therefore it does things like requires more energy to take one away, or it releases more energy when it gets another one. And as a result, it's also physically smaller. Conversely, when we're looking at going down the periodic table, this is perhaps the one where size is a little bit easier to talk about, because then we can actually just talk about values of n. And then we can just start to draw concentric circles and be like, oh, look, it actually gets bigger. And that's true. So as we increase our value of n, back to principal quantum numbers and what we learned about quantum numbers back in chapter 3, the greater the value of n, the larger that shell should be, or the larger that particular orbital is that houses that particular electron. The greater the value of n, the larger your atom should be, the larger your atomic radius. So atomic radius, as you go down the periodic table, is a reflection back to quantum numbers. Oh, look, they're back again. Quantum numbers. Questions so far? It's 5:15.
Yeah, so we have a couple over effective nuclear charge, and a good group of students asked if they need to calculate it or have to be able to know how to.
No. So in your textbook, your textbook has an equation for effective nuclear charge. The only thing I like about the equation is the concept behind it, because they'll do something like this for effective nuclear charge. And all they're really trying to tell you is that that's the regular nuclear charge, which for us, yes, would just be the number of protons. And then you are subtracting shielding. And that's your Z effective. So the only reason why I like the equation is because sometimes people will get a little bit stuck on, but how does Z effective relate to Z? What's really going on there? And all Z effective is trying to talk about the nuclear charge that's experienced by the electrons, especially in that outermost shell. So you're talking about Z effective being like the nuclear charge, but just taking shielding into account. The idea that the effective nuclear charge is going to be less than your number of protons because there are electrons in the way, that equation does that. So this is actually one of the few times where an equation might actually help you with the concept. But are we going to give you numbers for this and make you actually calculate it? No, because we're not going to do anything with these actual numbers. Much more useful to us as overall trends. But good question, good questions. Because yeah, the concept behind it is useful, but the actual equation itself is not. Other questions?
Okay, and then there are two that I'm going to conjoin together. Are there exceptions to the periodic trends you just mentioned? So for effective nuclear charge, atomic radius, and for electron affinity?
So the only other ones that we cover are the exceptions for electron affinity. So we will wind up, so we are not going to worry about things for effective nuclear charge or atomic radius, but we are going to worry about exceptions for ionization energy, which is what we've already talked about those, and electron affinity. So electron affinity which we've already seen has the same overall trends, is the energy released when an atom gains an electron. And this is still in the gas phase. Oh, actually, since chapter 4 and chapter 6 are together, you know what else I should have done? I actually also should have put electronegativity on this list. Guess what? It does the same thing. Because I was about to launch into a spiel about how it's different from electron affinity, but they're actually on the same exam. Dun, dun, dun. This whole 4 exams to 5 exams, I'm still not used to it. I've only had 1 year to practice 5 exams. So it's still a little bit different to me. But electron affinity, this is in the gas phase. So this is not electronegativity. This is electron affinity. This is still in chapter 4. Chapter 4. And this is going to have a similar variation in that P block. But in this case, what's going to happen is we're actually going to worry about groups 4A and groups 5A. So 4A, 2, 5A, there's 3. So now we're talking about what happens when you add an electron. And essentially, oftentimes adding 1 more electron actually does increase the stability of the element. So oftentimes an anion is a little bit more stable. often. So I'm going to make this note. First electron affinity adds stability, lower in energy. Second electron affinity does not. I'm going to put usually. So I think there's one or two where that still does happen. And essentially the reason for the second one is because you have to add a negative electron to an anion. So adding a negative thing to another negative thing turns out not that easy, because adding a negative thing to a negative thing, they do repel each other, and then you have other issues. So still talking about first. This is all about first electron affinity. Essentially what's going to happen is that the 5A without the extra electron has the half-filled subshell. So the electron affinity of 5A is lower than the electron affinity of 4A. 4A, this basically gets extra stability because of the half-filled subshell gained with the extra electron. So grabbing the graph, which is not nearly as pretty as the other graph. It's not its fault. It just isn't as pretty of a trend. But again, we can see that where for us, so 4A should be things like carbon. Scrolling all the way back up, 4A should be things like carbon. 5A would then be nitrogen again. So again, we see that we still have a high electron affinity for carbon, but the nitrogen is the one that's like way down here. So nitrogen, 5A, lower than expected. The other thing that happens in electron affinity, which again, when you think about it as things that want another electron, because really that's what's happening in electron affinity, is we're really asking, does the atom want another electron? And oftentimes the answer is sure. But there's a couple of times where the answer is no, 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 no. So 5A is a no, because 5A was already nice and stable. Didn't want anything else. No. And what you might also notice is here at the top, these are all halogens. These are all 7A. These are the ones that are like, yes, all I need is one more. I just need one more electron, and then I will be like a noble gas, and I will be so stable, and it'll be awesome. So your halogens have a really high electron affinity. Unsurprisingly, way down here are the other noble gases. So down here are the noble gases because they don't want one. They do not want another electron. No. So your noble gases are also going to have a low electron affinity because they don't want another electron. So these are all some of those exceptions that we would expect you to know. We would expect you to be comfortable with the idea that noble gases have a low electron affinity. I understand that the trend is increases from left to right across the periodic table, and a lot of that's true, but the noble gases are on the very far right, and they do not have a high electron affinity because the noble gases are stable just as they are. So this is part of the place where paying attention to the language becomes important. So someone from the pre-submitted questions had asked about electron affinity versus ionization energy, and the noble gases are a really good example of the difference between those two trends. So as I scroll back up to the periodic table, when you're looking at the noble gases and you're asking about ionization energy is where we're trying to remove an electron and we're asking how much energy is required to remove the electron. Well, the noble gases desperately want to keep everything they have. So the noble gas ionization energy is really high because they're trying to keep everything they have because they don't want to change. So the noble gas's goal is to not change. Goal, not change. So have a really high ionization energy because they do not want to change. They don't want to give up their electron. And then ironically, because of the definition of electron affinity, where electron affinity is asking how much energy is released, energy released means more stable. Well, the whole point of a noble gas is it doesn't want to change at all. So now suddenly something that has a high ionization energy, because it doesn't want to change, those same noble gases have a really low electron affinity for the same rationale. They still don't want to change. So those are some of the things that you just have to pay attention to, because what the element is after is usually a noble gas configuration, because a noble gas configuration is so stable. So whenever we're looking at exceptions to any of these trends, these are going to fall back on electron configuration, that idea of half filled or filled subshells, and where the stability really is. So asking about differences in trends, always a good call to go along with that. Other questions so far? I lost track.
No worries. So this question got a lot of likes, so I'm going to read it word for word just to make sure I get it all. But can you explain why EA is positive for the first and then negative for the rest, or if it's vice versa? Because Dr. D said it was opposite.
Okay, so here's the deal. So here's the deal. When we talk about energy released, whenever we talk about energy being released in chemistry, whenever we talk about energy being released, we would expect that change in energy to be negative. That was something that we talked about when we talked about electrons in atoms, and the fact that when you're going from a high energy to a low energy, energy is released. That's something that I know in my class, I don't know if I mentioned it in the exam review, but that you see the same effect when you talk about endothermic and exothermic reactions, which is when you go to a more, that basically when energy is released, that then we give that a negative value to denote which direction it's going. So, so if I'm right, I didn't sit in class, so I don't know. So if I'm right, Dr. Diekman probably described the electron affinity as being negative for a first electron affinity and being positive for a second electron affinity. I'll go ahead and write that down just so that we're clear on what came out of my mouth. So I'm actually going to write. I'm going to write a lot of words for just a minute. Dr. Taylor assumes Dr. D said. That'll also cover me later when someone looks back at these notes and they're like, well, this is what she said. I'm like, no, this is what I assumed. This is what I assumed he said. I don't know because I wasn't there. assuming that basically your first electron affinity is negative because it's becoming more stable. And then your second electron affinity, and beyond, actually, second, third, fourth, I don't care how many, because after the first one, these all do this, is actually positive. Because they're not more stable. No, yeah. To put not favorable. So that's what I assume. And this is actually why. It's because of how we usually define and denote positive and negative in terms of energy. Your textbook, and actually I meant to grab the textbook. I saw it in my office today and I was like, I should take that with me. I'm like, nah. Because your textbook, I thought basically was just trying to look at the magnitude overall. So I thought your textbook basically did like an absolute value of electron affinity. What we're going to wind up doing for the exam is focusing on the fact that it does increase as you go from left to right. And so basically, we're going to ignore the positive and negative bits of electron affinity because we're going to hold you guys to the pre-recorded videos, and that's Dr. Bacone on those videos, and I believe she uses this graph, which is actually using the absolute value of electron affinity. Dr. Diekman, I assumed, went ahead and did the more in-depth version of electron affinity to be consistent with the other messages that we've already given you about energy and the fact that whenever energy is released, it's a negative value. That is something that in my course, in my class, I think I got a lot of questions about ionization energy and electron affinity. And frankly, I ran out of time. Like I was gonna do this, but I also wanted to swap over to chapter 6, like at a particular time in class, and I missed that mark because I was answering other questions. So I was like, oh, I don't have time for the Pandora's box that is what value should this really have. So my assumption is Dr. Diekman did that to be consistent with the other things that we've taught you, which is actually accurate, by the way. Your textbook takes an absolute value is actually what your textbook does. Other questions on that? How do we do? Do they like it better or do they like it worse?
Well, more likes got on the question. So still a bit confused, but yeah, there was one question that popped up about electron affinity. Why does chlorine have a higher electron affinity than fluorine?
I got asked that last year and I looked it up and now I don't remember. Oh no, I don't remember. I remember very clearly being asked the same exact question last year. And I thought I looked into it because it bothered me. But that information is gone right now. So I am going to go with the truth, which is what I just said, which is I don't remember. Yeah, I unfortunately have to go with I don't remember because that's the truth. I did look at that last year. Somebody asked. I'm going to scroll up to my ionization energy graph and see where. No, chlorine falls nice and neatly with fluorine and ionization energy. It's just electron affinity that it's a little bit higher. Yep, got to go with I don't remember. I'm sorry that that's a bad answer, but that's what I've got because somebody asked me that last year and I don't remember. Anything else?
I think we're good to go from here.
Okay. And I will remind y'all, so if you guys are unpleased with I wasn't in Dr. Deacon's class, so therefore I don't know. I will take a moment to remind you guys that in our e-learning site in the 701 section, we have a folder for exam reviews. And Dr. Diekman has an exam review Wednesday night. So if you guys would like to ask that question of Dr. Diekman, he'll usually take questions from you guys, or you can email him that question and say, hey, in your review, I would really like you to talk about electron affinity and energy and positive and negative values and all of that jazz, and let him have at. And then I will be super glad that I said Dr. Taylor assumes Dr. D said, because I don't actually know what he said. I just think I know. So yes, you could definitely ask Dr. Deakin that question. What I'm going to do is come back to this list I had at the very beginning. Irregularities and trends, differences between ionization energy and electron affinity. So I'm going to start making myself some little check marks. Okay, we did that. We did the differences. I honestly do not know what the electron affinity equation is. I'm going to hope that that was that Z effective thing that we looked at. Z effective and atomic radius, I think we did that. We did all of those. We did stability. We did quantum numbers. We did periodic trends. Oh, Lewis structures. Let's talk about Lewis structures. I've got like 20 minutes. Let's do this. So, Lewis structures. Oh, I did ignore electronegativity. Yep. Just gonna leave that up there while I grab what I wanted to grab. So here's the deal. Lewis structures. So there's a list of general rules of thumb, how to draw Lewis structures. That's what this list is it's basically information on how to draw Lewis structures. The reason why I'm going to bother talking about this, because if you have already had AP chemistry, you may have already tuned me out. Gosh, I hope not, because there are some really weird structures we can ask you to draw. And if you know how to use this list, you can draw anything we ask you to. And if you do these, you'll be just fine. There are a couple of times where I've seen those folks who've had AP chemistry that are super confident, and they're like, they drew something super basic that I already know how to do. I'm not going to pay attention. And then we do something like give you guys something that has an odd number of electrons. And then they get a little bit upset. But if you follow these rules, you'll be just fine. You can even do odd numbers of electrons with this set. So in general, yes, we do expect you all to be able to draw Lewis structures. One of the questions was about what could you possibly do though, because you're not going to make me upload a file on the exam, which is true. So I'm going to go ahead and, since I mentioned it, actually, no, I'm going to cheat and draw something more basic because it's got all the things I need on it. So I'm just going to draw water. You've probably already seen water, but what we could essentially do is we could give you the formula, which I don't know if you noticed, but we skipped over nomenclature. So we can't actually name anything. We have to give you the structures. We have to give you the formulas for these. And what I could do is I could ask things like, how many valence electrons are in this molecule? And honestly, you don't have to draw the whole Lewis structure to answer that question, but you would need to be familiar with Lewis structures, because the very first thing is to count the number of valence electrons for all of the atoms. So since that's the very first step in drawing Lewis structures, we expect that you can do that. So as far as how that's going to work, all we're going to do is take our periodic table. Apologies for all of the scrolling. So much scrolling. And from our periodic table, what we can then do is use the number of valence electrons. Those are going to be the outermost electrons. But usually these little numbers up at the tippy top will tell us what those are. So for each hydrogen atom, that's 1, and for oxygen, that's 6. So I have 2 hydrogens, so that's 2 times 1 electron, and I have 1 oxygen, so that's 1 times 6. It's 2 plus 6, which is 8. Then we'll talk about things like symmetry being preferred. So basically put all of your atoms out so they can all hang out together. Put everything together, because if they're hanging out, they're going to be bonded together. Said it was a molecule, it's bonded together. So there's 2 electrons in every line. So I just used 4 electrons. That gives me 4 left. And then I can put lone pairs on the central atom if I have extra. And that was actually following these rules. So I counted the valence electrons. I arranged the atoms with symmetry, connected everything by single bonds. Completing octets for outermost, I was using hydrogen. Hydrogen only has an octet of 2. I know that always sounds weird when I say it. And if extra electrons remain, I added electron pairs to the central atom. So here's my Lewis structure for water. Now here, so I could have asked how many valence electrons are in the molecule. That actually is 8. So that was that first thing I counted, and we figured out. Then there are other things that I can do. So I could ask other questions like how many single, double, or triple bonds are present. And I realize that for water, this may seem silly, but again, for double bonds, it has none. For triple bonds, it has none. For single bonds, I have 2. So I could answer questions about the molecule without actually asking to see it. Likewise, I could ask things like how many lone pairs. And do be careful with some of these, because for water, it does not matter, because I could ask how many lone pairs are in the molecule. But I could also ask something that is really similar but different. I could ask how many lone pairs are on the central atom. And for what we just drew, for water, this is the same. So for water, the entire molecule just has 2, and those 2 just so happen to be, this is a lone pair, by the way, and this is a lone pair. So for this particular molecule, lone pairs on the central atom and lone pairs on the molecule are the same. If we had a different structure, and this is actually one that Dr. Diekman draws in his video. It's in the chapter 5 and 6. It's video part 3. Yes, part 3. He draws carbon tetrachloride. So just realize that if we were answering these same 2 questions for this molecule, if I was talking about the molecule, well, then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if I was asking about the central atom, well, my central atom is carbon. The central atom is the atom in the middle. And then that is a big 0. So, and this is also that part where, so one of the things that we can do is we can ask you questions about the molecule that would require you to have drawn it correctly, and then we'll ask you questions about it. That's one thing we can do. Some of the other things that we can do is also realize that we can do things where we could actually give you multiple structures and ask you to analyze them. So this is one where we especially often do this with formal charge, which I realize you may or may not have heard of formal charge yet. This is in video, this is Dr. D, this is, video part 4 is where that one is. But formal charge is an electron accounting method, essentially. And it's another really nice way for us to ask you about Lewis structures, and either you could have drawn it yourself, or maybe we've actually drawn it for you. So for example, I'll actually just do one. So we can actually look at formal charge on something like this chlorine atom. So formal charge, there's a bunch of different ways to define the formula. Essentially, I picked up from a PLTL leader years ago. They used to describe formal charge as what it brought minus sticks minus dots. The goal is to look at valence electrons and then figure out how many electrons the atom actually wound up with, minus the electrons the atom wound up with. Formal charge is essentially trying to undo the sharing. So all of the things with Lewis structures are all about atoms sharing electrons. Formal charge basically asks, like, so if it wasn't sharing, like, how happy is this atom really? So for this chlorine, valence electrons, I'd look at my periodic table, find chlorine, find it's in 7A, and I would say, okay, so this chlorine atom has 7 valence electrons, and then from my sticks, it has 1 stick. Essentially, we're pretending that even though there are 2 electrons in this single bond, for formal charge, we actually assume that the chlorine has 1 and the carbon has the other. So that's 1 for that. And then dots, we basically count all of the electrons in the lone pairs, 6. So you have a formal charge on the chlorine of 0. And there's a couple of different formal charge equations because there are a couple of different ways to describe how you figure out, okay, I have a bond and I'm basically going to give half of the bond to chlorine and half of the bond to the carbon. There's a few different ways to say that. Same thing when you talk about the lone pairs. Some people will talk about, well, it's the number of lone pairs times 2. Some people will talk about it as being the dots. Some people will talk about it as being all of the non-bonding electrons. So whenever you talk about formal charge, there's a few different ways to describe exactly what you're doing. But again, the underlying concept is to look at what you have and essentially try to separate it out and be like, okay, I know they're sharing, but what if they weren't sharing? What if the sharing stopped? How happy would this atom actually be? So that's one example of different kinds of analyses that we could have you do for Lewis structures. That's not the only ones, but that at least gives you guys a little bit of an idea for what we might do. And there's a couple other topics that are still in chapter 6 that would also let you guys analyze things. Are there questions? Because I was supposed to ask 3 minutes ago and I didn't. Questions?
No worries at all. So we have one. I believe you mentioned slides earlier, and someone's asking if they can have access to them if they're not in your class.
So yes, you can. You have to remind me often enough that I actually do it, because I'm pretty sure there was somebody else that asked me for something before the first exam, but they asked me for like 2 different things, and I successfully got them one thing and not the other. And I feel bad about that. I do feel bad. I failed. And now I have to go see if I can find that person. So yes, you can, but sometimes you just have to email me more than once to make sure I actually do it. Slides are a little bit easier because I used to just have a Dropbox folder for that, and I probably still do. I have to see if it's updated. Because someone else was asking me for something that I've been making for my class, but I'm making them as I go along, and Luckily I've uploaded them to e-learning, but aside from the fact that I've luckily uploaded some things to e-learning, sometimes I have to go get them out of e-learning because my electronic file system is not good. If y'all have never been to my office on campus is not super organized. That unfortunately carries over to other aspects of my life. So yes, you can have to shoot me an email and get me to respond. Sometimes it's tricky. Other questions?
Okay, perfect. And then one came in when you were talking about Lewis structures. Should we always check the formal charge for every Lewis structure we draw?
Yes. Yes, you should. There are times where you should get faster at it. So let me give you the example. So we were talking about formal charge. Let's look at hydrogen. So hydrogen has one valence electron. And if we were to give hydrogen credit for that one electron in that one bond, we would just subtract 1, and that would be 0. So hydrogen, as long as it has one single bond and that's all, hydrogen's good to go. So it's always worth checking, because if you did have a double bond to hydrogen, that is bad. Hydrogen does not get double bonds. It can't handle it. So it is always worth checking, but it's oftentimes something that the more times you do it, the more you'll get to the point where you wouldn't actually check hydrogen, because you would just look at hydrogen and say, oh, I only have a single bond to hydrogen. I am good to go. And that often happens the more practiced you are. Sometimes you can start doing things a little bit faster. So oxygen. Now, granted, I realize that a lot of you have not seen formal charge before and you're learning it as I'm doing it right now. But for oxygen, so oxygen has 6 valence electrons. Then it's got I'm going to split up its 2 sticks. So it has 2 sticks, and then it has its 4 dots, which is also 0. So a lot of times with formal charge, you'll see that every atom oftentimes has a 0 formal charge. That's not always true. Sometimes it can have a positive or a negative, but you want the formal charge on each atom to be as low as possible. So oxygen oftentimes has those 2 lone pairs. So in general, oxygen often, again, not always, but often, has 2 bonds and 2 lone pairs. That is the normal state of oxygen. So sometimes that's a double bond and 2 lone pairs. Sometimes that's 2 single bonds and 2 lone pairs. And it doesn't mean that that's its only option, but a lot of times for things like formal charge, again, the more Lewis structures you practice, the more you'll start to see some patterns that tend to arise. But yes, especially as you're starting out, doing formal charge for your Lewis structures is a really good habit for 2 reasons. One, because that does assure that you found the right structure. So one of the things that I had skipped, but the Lewis structure with the lowest formal charge is the most stable and preferred. So when you're trying to figure out, did I do it right? Formal charge is usually the way to go with that one. So that's one reason. And then the other reason is that point that I brought up formal charge, which is, since we're not going to have you guys draw and show us what you drew, us asking you about formal charge is a common thing we ask. So the odds of us asking you a question about formal charge is really high. It's really, really good that we would likely do that, because that's a relatively straightforward question for us to ask. It's something we expect you know how to do, and makes a really easy multiple choice question, because usually formal charge is like 0, -1, +1, 2. Formal charge is usually pretty low, so it doesn't have that many options to mess with. other questions that came up?
Yes, so this question has popped up quite a bit, so this person really wants me to ask.
Okay.
Could you go over spin and how to find out the spin for elements?
The spin for elements, diamagnetic and paramagnetic. I'm gonna hope that's what this person is looking for, because so m sub s is usually what we refer to as spin. M sub s is a quantum number. Now, on this exam, you guys do have to remember the Pauli exclusion principle. I understand that Pauli exclusion was a thing that was in chapter 3, but for us, the Pauli exclusion principle is part of what's been in all of our orbital notations when we've been doing this one up and one down. So this notion that we've been drawing an up arrow, up and down arrows, is actually indicating your m sub s value, which is indicating spin. And your Pauli exclusion principle is that idea that each electron has a unique set of quantum numbers. So, and that is also still a valid thing to show you in orbital diagrams. So for example, if we were looking for a violation of the Pauli exclusion principle, which yes, I'm going to start abbreviating kind of randomly, what we would be doing is we'd be looking for something where I have like up arrows or all down arrows. So these would relate to a violation of the Pauli exclusion principle. Now, the reason why I sounded a little bit startled by the question is because spin refers to a quantum number, and it refers to a quantum number that's very specific to an individual electron. So whenever we're talking about spin, that actually is that last final quantum number that relates to an electron. So whenever we're really doing spin, this is usually to ID 1 electron. So the part of the question that I'm a little bit fuzzy on, uncertain on, is I think the question stated like the spin of an atom. And that one I'm confused on because usually we don't talk about spins of whole atoms, because atoms, aside from hydrogen, have a whole bunch of electrons. And since you're going to have electrons with either spin, you don't necessarily have a spin for an atom, you have spin for electrons. So what I'm assuming the person was talking about either was a Pauli exclusion principle, which we chatted about a little bit, or they were talking about diamagnetic and paramagnetic. So diamagnetic and paramagnetic, diamagnetic is the one where I'm going to describe this as for every up there is a down. In part because I like Sword in the Stone. And because if we do ask you guys something tricky, this is actually a easier way to understand what we say when we say electrons are paired. Paramagnetic then is basically an atom has at least one unpaired electron. And the way that you figure this out is you figure these out with orbital diagrams. So if I was talking about helium, for example, my orbital diagram is my 1s and my 2 electrons for helium. If I was talking about carbon, then I would have my 1s and then my 2s and then my 2p. So my helium, we would describe as being diamagnetic because all of my electrons are paired. For every up, there is a down. For carbon, on the other hand, I have these unpaired electrons. And so therefore, I would describe this as being paramagnetic. So when we're asking for diamagnetic and paramagnetic, oftentimes we will give you a set of elements and just ask you which of the following are diamagnetic or which of the following are paramagnetic. And then that's again where you would be going back to neutral ground state atoms. So that would be part of the question, because you would just be looking at the periodic table, going from left to right and looking at where your electrons go and if you have things that are paired or unpaired as you go along. The other option is that we would draw them out for you. And so that's another option where we could draw you out a couple of different options and then ask you which of the following are diamagnetic or paramagnetic. Usually diamagnetic and paramagnetic are terms that you just have to remember that we talked about. So oftentimes those kinds of questions are not that bad, aside from the fact that, especially by the time we get all the way through Lewis structures, and we go through Lewis structures and we talk about things we didn't talk about this evening because we're out of time. So we didn't talk about electronegativity. We didn't talk about bond polarity. We didn't talk about percent ionic character of a bond. We did not talk about resonance structures. We didn't talk about something else at the end of chapter 6. What is it? It's going to bother me. That's resonance. Maybe it's just resonance. Oh, bond order, because bond order goes with resonance. Oh, and some of the really weird octet rule thingies. The definition of a coordinate covalent bond. There's my odd numbers of electrons. And there's my version of the periodic table that has some funky exceptions because there's not actually that many elements that actually strictly follow the octet rule. There's only 4 of them. I guess neon does too. I should expand this to neon. But neon doesn't really form any bonds. So, you know, but neon is pretty strict with its octet. So there's other stuff in chapter 6 that, again, we're out of time for. So oftentimes by the time you're done with chapter 6 and you've been drawing all these Lewis structures, suddenly somebody asks you a question about diamagnetic and paramagnetic, and you're just like, what now? What? So yeah, so the main trick is to remember diamagnetic and paramagnetic. They are things. Remember them. We will ask you a question about them. I almost promise. I can't exactly promise because, you know, the exam is not done yet, but I can almost promise that we'll ask you one question about diamagnetic and paramagnetic. I can also likewise almost promise that we'll ask you something about resonance and an expanded octet, because those are also questions we usually like. Okay, I know we're out of time, but are there any other questions I can answer before we go?
So we do have some, but we will be sending them out to you, and we'll be letting all the students know the responses that you have.
Okay. Sounds good. All right. Well, then thank you all for showing up this evening, and have a good night. It's time to wander over and find dinner.